In this video, we're going to use the Lux deep learning framework in Julia together with the Zygote automatic differentiation engine and the package optimizers in order to train a very simple neural network, a multi-layer perceptron, to mimic the sine function from data. For this, we will create an artificial dataset that you see here on the right. Then we will initialize the network, and initially it will predict a rather stupid output. Then we define a loss function, use the automatic differentiation engine to provide gradient information and iteratively update the parameters of our network. We can then see the loss of our optimization going down, and ultimately we will then find that the prediction of the network approximately looks like a sine function. Let's get started. Hi and welcome to this new video and another installment in the series of training neural networks to mimic the sine function in various languages and frameworks. And this time we want to look at the Lux framework in Julia. This is a rather new addition to deep learning frameworks in Julia, and I like it in particular because it provides an explicit parameterization of networks. So you always keep your parameters and your states of the network separate from the architecture, and I think this really helps in a lot of places conceptually, especially when it comes to scientific machine learning. So let's get started with importing our packages. So first of all, of course, we will need the Lux package. Then we need the random package in order to initialize our network. We will use the Zygote package. Zygote is one of the automatic differentiation engines in Julia. It's one of the more mature ones that provides the reverse mode, which we will use in order to backpropagate and get gradient information. Then we will also need the optimizers package. This provides typical gradient-based optimizers like the Atom optimizer, but here we will just use a plain gradient descent. Then I also want to use the plots package, obviously to plot. Then we will need the distribution package here for creating our toy dataset. And then I also want to use the statistics package, which provides the mean function. I'm here in Visual Studio Code together with an interactive REPL session, and I can shift enter a line in order to execute it. And you see this arrow indicating that this one is executed, so it's performing the import. And also you see here in the bottom that the REPL is updating. And here we go. This imports our packages. Afterwards, we can now define our constants or hyperparameters. Let's say the number of samples for our toy dataset shall be 200. Then let's define the layers of our multi-layer perceptron architecture as being 1, 10, 10, 10, 1. So we have one-dimensional input. So this is the x to the sine function, and we have a y-dimensional output. This is the y as if we applied the sine to x. And then we have 3 hidden layers with 10 dimensions. Then let's define the learning rate, which we will use for our gradient-based optimizer. And this one is 0.1. And then with this learning rate, we will perform 30,000 epochs or optimization iterations. So let's also shift enter all these constants. And here you see Julia is responding with the particular value that is created here. Then in order to make our randomness reproducible, we will create a pseudo-random number generator. Let's call this our pseudo-random number generator. And I want to call this RNG. And there are 2 major options. We can either use the Mersenne twister from the random package, or here I want to use the Cro0 one, which is the recommended one in newer Julia versions. It requires a seed, and I want to start at 42. Shift enter also gets us the generator. Then we will draw a toy dataset. And for this, we will first draw the X samples, so the inputs. And for this, we will use rand in order to produce random samples. Then we will provide the random number generator. And then we will define the distribution from which we want to sample. And this shall be a uniform distribution between 0 and 2 times pi. And the shape of the array that we want to sample is 1 by n samples. And this is because we follow the Julia convention in which for tabular data, we have the spatial dimension first, and then we have the batch dimension. And then let's create some noise for the y samples. Let's call this the y noise. And we will use rand and again, the random number generator. By the way, these rand functions, they are mutating. So the state of the pseudo-random number generator is updated every time we use it in order to create random samples. Okay, for the noise, we need a normal distribution, and I want to center it at 0 and have it with a standard deviation of 0.3. And then I want to draw n by n sample values because we want to corrupt each of the samples individually. And then we will get our y samples by calling the sine function element-wise on the x samples matrix. And then we will element-wise add the y noise. Okay, let's take a look at the data. So we will use a scatter plot and we will provide the x samples. And since the x samples are now in this spatial by batch dimension, we need to flatten them into one vector. And this can be easily done by just using the angular brackets and then using the colon operator to flatten it into a vector. And let's do the same for the y samples and add a label and just call it data. Okay, let's shift enter the x samples, the y noise, the y samples, and the scatter plot. Here we have it, and we see that this is some scattered points, and of course they somehow follow a sine function in between 0 and 2 pi. Next up, I want to define the architecture of our neural network. So let's write down a heading and say define the model architecture. And I want to call this the model. And since we're using a simple feed-forward neural network, it makes sense to express its architecture in some form of a chain of functions. And this is also here. So we use the chain command in order to chain layers or building blocks of our neural network. And in essence, what we have to chain are the layer transitions. If we look at the layer constants again, we see we have 5 layers in total, out of which are 3 hidden layers. And for 5 layers, we have 4 layer transitions. And out of these 4 layer transitions, we have 3 which we want to have with a nonlinear activation function. So from 1 to 10, from 10 to 10, and from 10 to 10, we want to have them with a nonlinear activation function. And then we have a final layer transition, which maps into the dimensionality of our output, which is 1 dimensional or 1 spatial dimension. And there we do not want to have a nonlinear activation function. How can we do that? So for this, I want to use some sort of a list abstraction. So I will create a list or something like an array using the angular brackets, and then say we want to do dense of fan in maps to fan out. And here I'm using this pair command in Julia, which uses the equal sign and then the greater sign in order to indicate an arrow, so that we have a mapping from fan in to fan out. And then I can also specify the activation function, and I want to use Lux.sigmoid. Sigmoid is not exported by Lux, so we have to access it by Lux. And then we can do a list abstraction and saying for fan in, fan out in zip, and then we will do a zip iteration of an iterator which goes from the beginning to where we want it to go, and then another iterator which goes from the second element to where we want it to go. So we will say zip of layers indexed at the beginning all the way to the end -1, and layers indexed at the second element going all the way to the end. So then we will iterate basically over each pair that we have as transition. But now we have to be careful. This would produce a neural network which also had the sigmoid as the activation function in the very last layer. So instead of going to the very last layer, we will go to end -2, and here we will go to end -1. And then we will add another dense layer and say dense, and this is now the last layer transition, which is from layers at end -1 paired with layers at end. And it uses as the activation function the identity. Or we could have also just left it out here and it would use the identity function. And by default, these dense layers will also use a bias. And we can also check what kind of initialization algorithm they're using, a chloro uniform and a 0 initialization for the bias. Okay, now we need to do one last thing. So here we have the chain, and basically the API of the chain is that it takes an arbitrary number of layers, but we are now providing it not with our 4 layer transitions, but rather we are providing it with a list of layer transition and layer transition. So we need to split the list into a certain number of entries, and we can easily do that with the 3 dots. If you come from Python, then you might have seen that you can do this with an asterisk in the beginning of your list. Okay, this should give us the model. And if we did everything correctly, now this will also print a nice summary of the model. So we have 4 layers, or you could also say layer transitions. And as said, the first 3 ones are with the sigmoid activation function. And then we also have the last one without one. In total, our network has 251 parameters. So it's a very small neural network. Okay, and now the beauty of Lux comes into play in that the network is just the architecture. So it just says how the computation is performed. It does not store parameters, so weights and biases, but it also does not store states. For instance, if you had some sort of a dropout or some other stateful neural network. So this is the next state. So we will initialize the parameters and also the layer states, but those are only relevant if we had a stateful layer. So only relevant if neural network, or let's break into the next line, neural network was stateful. And then we will get the parameters and the layer states by calling Lux.setup and provide it with a random number generator and the architecture. And then it will use the initialization routines that we also have defined in the architecture to produce an initial guess of the parameters. And here you see, this is basically a named tuple with the layers, the weights, and in there we have the matrices with the biases. And the layer states, if we take a look at that, this is just an empty object. So it is just a collection of the layers and then empty named tuples because we don't have any states here. So we could also just ignore them for now, but we will keep them through just for having the most general case. So let's make a prediction with the initial parameters. So let's call this the Y initial prediction. And for this, we have to query our neural network. And this can be done by taking the architecture and using it as a function, which takes the input and we are providing it with the examples, but it also has 2 additional required arguments, and those are the parameters and the layer states. And if you've ever worked with a deep learning framework which has another approach, where the parameters and the layer states are part of the architecture, of course you wouldn't have to explicitly provide them. This is of course a little downside that you always have to carry the parameters and the layer states through, but you can be very sure that the model or the architecture is pure. And you could also have multiple parameters at the same time and call them with different ones. So there are very interesting applications for that. Let's make the prediction. Here we go. And then let's try to scatter into our existing graph by using the exclamation mark and then do x samples at colon and y samples at colon. And then let's add the label and say it is the initial prediction. But before I execute that, we have to think about that. It will not work actually, because if we call the model, so imagine our model was stateful and we called it on something together with parameters and layer states, it would update the layer states. But since the architecture does not have the state of the network, we need to explicitly get the new state back. So the parameters are of course not updated, but the states would. And this is that whenever we query a Lux model, it also returns the updated layer states. And we will just save it in the same variable. So we will actually overwrite the layer states. So when we query the model, we get back the initial prediction and the overwritten layer states. As said here in our case, we have no layer states, but just in general terms. Okay, then we will try this again, Shift Enter. And now let's plot. Okay, of course, yeah, I did this wrong. This should be, of course, the Y initial prediction. And then we also need a new plot of the data points. And here we go. Now we have our initial prediction and we see this is more or less a straight line. And that is of course a very bad estimate for the sine function, but for us it's a good estimate as the beginning of the optimization. No oscillations, no crazy magnitude, and that's a totally fine start. Okay, let's define a loss metric. And let's say this is the forward function. So we are using automatic differentiation. So we only need to define a primal or forward function, which somehow maps our design variables, so the parameters, all the way to a scalar valued loss. And then we can just get a gradient estimate by the automatic differentiation engine. So let's call this the loss function. And this loss function shall take parameters and layer states. And then what it does, it produces a Y prediction as well as new layer states by querying the model, which it captures from the environment. So it is also in some sense a closure function. So we use the model that we have in the higher scope and query this on examples, which it also captures together with P and LS. And then we will get the loss by 0.5 times the mean of Y prediction minus Y samples, or more precisely the element-wise difference, and then we will element-wise square that. So we get some sort of a mean squared error. And then this function shall return the loss and the new layer state, and then we can end the function. And of course, this is again a little bit unintuitive. We also not only return a loss, and we also provide the new layer states, because whenever we query the model, we also need to make sure that the updated layer state is propagated back to another scope where we call that function. Of course, again, here for us, not really relevant, but if you had stateful models, that would be relevant for you. And as we will see later, this also brings a little bit of small headache when we apply the automatic differentiation to it. Then next up, we will prepare the optimizer. We will just use plain gradient descent here, but you can swap for Adam if you want, but swap to Adam if you want. So the optimizer library provides a lot of routines that you could use here. So let's define the optimizer by being the descent optimizer. That's how it's called here, and together with the learning rate. And then we can initialize the optimizer state by saying optimizers.setup the optimizer together with the parameters. Because what is actually that we are optimizing over? It is the parameters of the network. Then we can provide the train loop, and we will record the loss history such that we can visualize it later on. So let's say this is an empty list for now. And then let's do for epoch in 1 to n epochs. There we first perform our forward and backward pass. And for this we need the automatic differentiation engine. And we need to use the pullback routine, so a rather low-level approach to automatic differentiation. How does that work? By the way, if you want more details on that, I also have a video linked up here going into pullback in more detail. But what does it do? It needs a function. So we will give it the loss function as well as the primal points at which it shall evaluate it. And this is the current parameters and the current layer states, because we are doing an optimization over the parameters. Within these epochs, the parameters change. So these are our current values that we have here. And then what does that function return? So first of all, it returns the loss and the layer states, or the new layer state, but we will again just override them. So basically it performs a primal execution. So as if we would call loss function on our current parameters and layer states. But then it also returns a pullback or a backwards function, which takes cotangent estimates on the same outputs it produces with the same shape as it had outputs, to then get cotangents on the same shape as it had inputs. We will demystify that in a second. We just need to make sure that we place parentheses around here in order to use the tuple unpacking, because it returns basically two entries. First, the primal output, and the primal output also was a tuple with two entries, and then this backward function. Okay, next up. Now we need to use this backward function. So typically what you would do if you only had a scalar output, you would call it on 1.0. So then you would say, okay, my cotangent loss value is 1. So I will start my reverse mode automatic differentiation with the value 1. That's typically what you would do. And then you would return a gradient for you. And this gradient you could then use in the optimization. But here we had two outputs. We had a loss and layer states. So we also need to provide cotangent information on the layer states. But if we do not want to do that, we can also just say nothing. So we don't provide it here. And now we need to pack that into a tuple because we need to match again the signature of the output of the primal function, which was a tuple. So we also use a tuple here. And then this returns with the signature of the input of the primal function, which was parameters and layer states. And the cotangent on the parameter is the gradient. And the cotangent on the layer state, we're not interested in it. So let's use a placeholder variable here. Okay, how to digest? Let me try it once again. So we have the pullback, which is from the Zygote automatic differentiation engine, which takes a function which shall be transformed, which is our loss function. And this is now evaluated at primal inputs. So the forward pass, which we would do anyways, because we need to say how good our current parameter guess is. And then what it does, it produces the primal output and gives us a backwards function or a vector Jacobian product function that can be called with the same signature as the output of the primal function to produce cotangents with the same signature as the input of the primal function. But we use some placeholder here because we don't need cotangent layer states, and we also don't provide cotangent output layer state or new cotangent new layer states. So this is essentially what we will get, the gradient for our optimizer. We can then use optimizers.update on the optimizer state, the parameters, as well as the gradient to perform an update step. So in our case, with a plain gradient descent, this is just current value minus learning rate times gradient. And then what we will get back is the updated optimization state. So we will just overwrite the variable as well as the updated parameters. So we will also just overwrite the variable. Then we can push the loss into the loss history for our visualization. And then every 100 epoch. So if epoch is divisible by 100, I want to, this of course takes 2 equal signs. Then I want to print it out. So let's say print line and then use an interpolated string with saying epoch is the current epoch and loss is the current loss. And then let's end the for loop. And then I think we need quite some shift enters. So we need to shift enter the loss function, optimizer state, and yes, then the loss history, and then we can run our loop. Hopefully it works. Let's see, this takes a little bit because the Zygote automatic differentiation engine is rewriting the source code, not rewriting the source code, but is taking the source code of the loss function and then rewriting it to get the backward function. And the very first time it does so, this takes time, but here we go, loss is going down. By the way, this is on the CPU here. So yeah, now we are reached at 30,000 epochs. Then we can first of all plot the loss history. So let's do a plot loss history and say that the y scale should be logarithmic. Okay, maybe we should provide logarithmic 10. Okay, here we go. And there we have our loss plot. So we have in x the number of optimization iterations, and we see the loss is going down, and we are mostly converged with our network. And then let's use the final parameter state to plot the final prediction. So we have the y final prediction, and then let's use a placeholder for the updated layer states, or maybe let's make it more clear and override the layer states again and call the model on x samples, parameters, and layer states. And then again, we will first scatter our ground truth data. So x samples colon y samples colon and add the label of being the data points, and then scatter exclamation mark on x samples colon and y final prediction colon, and the label is final prediction. Let's see. Okay, here we go. This is the output that you already saw in the intro. So we have again in blue the ground truth data points, and then in orange how the network interpolates them. And this is almost a sine function. Arguably, across all the videos we've seen in the series so far, this is probably the worst sine function. But of course, based on the simplicity we try here in this script, this is still a good result. And of course, there are many more things that one could tweak here. Let me quickly summarize. So in this video, we used Lux, which is a relatively new deep learning framework in Julia. We created our toy dataset. Then we defined the model architecture via the chain command. And the chain takes all these building blocks. You could also use convolutional layers, whatever you like. And then we initialized or set the model up by producing initial parameter guesses and initial layer states. And the very nice point, I like it a lot. Of course, it can be a bit unhandy, but it is definitely something helpful in a lot of applications. The parameters and the layer states of the network are treated explicitly. So we need to carry them through all the computations we're doing. So when querying the model, but also more importantly, if we do reverse mode automatic differentiation over the model, it takes a bit of a headache, but once you've seen that, it probably makes sense. And then we used a simple training loop with the gradient descent optimizer, updated the parameters, iteratively got our loss down, and then got a really ugly sine function out of it. But still, we learned something, and this is very important. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed this video. If you did, then please leave a like and consider subscribing to the channel. You might also be interested in watching the series of training these multi-layer perceptrons to mimic the sine function. So you will find that linked in the bottom right. You will also find another interesting video in the bottom left. I hope you're interested in that, and I hope to see you in one of the next videos.